Good morning, everyone. Today I'm going to talk about inference in first-order logic. In this chapter, first we'll look at the first-order logic inference rule, the two inference rules, and a very important inference rule, the general modus ponens rule. And then I'll talk about unification, which is a very important technique for the automated reasoning algorithm. And then I'll talk about two automated reasoning algorithms, the forward training algorithm and the backward training algorithm. And next, I'll talk something about the logic programming language Perlock. And finally, I'll talk about the resolution technique, which is the general technique for automated reasoning. The inference rule, the main inference rule includes two. First is the universal instantiation rule, and the second is the existential instantiation rule. And based on these two inference rules, we can construct a automatic reasoning technique called propositionalization technique. This is a very inefficient technique, but it is very important for us to understand the two inference rules. And then I'll talk about the general modus ponens rule, which is the key technique for the two automated reasoning algorithms. First, the universal instantiation rule. It means that if you are given a universal quantified sentence, you can apply a ground term, any ground term, to the sentence and generate a new sentence. The sentence will be valid and you can add it to the knowledge base. And the existential instantiation rule, if you are given an existential quantified sentence, you can apply a constant variable k to the sentence and you can discard the original rule. And the newly generated sentence, this one, will be valid in the knowledge base. This process is called columnization. This is a special case of columnization, as we shall see when we are converting the CNF in resolution. We'll talk about later. When we compare these two rules, for universal instantiations, you can apply the rule many times to generate many different sentences, and the original sentence cannot be discarded unless you have enumerated all the objects in the model. But for the existential instantiations, this rule can be applied once, then the original sentence can be discarded. The resulting knowledge base is not logically equivalent to the original, but is inferential equivalent. Based on the two rules, the universal instantiations and existential instantiations, we can build an automated reasoning technique called propositionalization. We can turn each existential quantified sentence, replace them with each of them with one instantiation, and replace the universal quantified sentence with the set of all possible instantiations in the model. And then we can apply any of the complete automated reasoning algorithm in propositional logic. But the problem is, if the knowledge base contains function symbols, the number of ground terms may be infinite. For example, if we have a function symbol father x, which means the father of x, we can generate infinite number of father in this way. The father of Peter, the grandfather of Peter, the great-grandfather of Peter, etc. There is no end. But even for such knowledge base, we can each sentence that is entailed by the original first-order knowledge base. There is a proof revolving just a finite subset of the propositional knowledge base, which means when we are trying to generate a proof for a query, we can first apply the constant symbols, and then we apply the terms of that one, which means we apply the function symbol once, then we apply the function symbol twice with recursion, etc. And step 3, etc. Until this process repeats until the query is reached. But the problem is, if this query is not entailed by the knowledge base, the algorithm cannot tell, and will never stop. But so there is a theorem here. The algorithm does exist that says yes to every entailed sentence, but no algorithm says no to every non-entailed sentence. And the general modus ponens rule. If we have atomic sentences, pi and p pi I and q, and we have a substitution that make the premise of this implication identical to the conjunction of facts in the knowledge base, then we can apply this substitution theta to q and generate a new valid sentence. For example, here are the two facts, and here is the implication. We can apply the substitution join to x and join to y, and we can make the premise of the implication identical to the conjunction of these two facts. Then we can apply the substitution to the conclusion of the implication, and we can get the query we want to get. John is an evil. This rule, the general modus ponens rule, is sound. First, by universal instantiation, we can apply a substitution and generate a valid sentence, and the conjunction of them will also be valid by point 1. And because the substitutions makes the conjunction of facts and the premise of the implication look identical, the conclusion of the implication can be inferred. So the conclusion holds, which means the general modus ponens rule is sound. And then the unification technique. First, I'll talk about what is unification and why we do need unification. Then I'll talk about the most general unifier. Next, I'll talk about the algorithm to find most general unifier. And I'll talk about the implementation of tell and ask operation in a common knowledge-based agent. And finally, I'll talk about the substitution lattice. First, what is unification? Unification is to find a substitution that makes two sentences look identical. Why do we need such an operation? We need such an operation because we want to use the general modus ponens rule. Here are 4 examples of unifications. The first 3 examples are easy to understand, but I would like to talk about the 4th example. You can see here the unification process fails because the variable x cannot take 2 different constant symbols at the same time. But the problem is actually they can be unified. If we apply Elizabeth to here and join to here, they look identical. The problem is the 2 sentences being unified contain variables that are identical. So if 2 sentences are to be unified, each variable must be distinct. This is what the standardized operation wants to do, to rename the variables, to avoid name clashes. There could be more than one unifier for a pair of sentences, and there are unifiers that are more general than the other unifiers. For example, for the pair of sentences here, we have two unifiers. And this one on the left is more general than the one on the right. Because if we apply the substitution join to Z, we can obtain the one on the right. And for every unifiable pair of expressions, there is a single most general unifier that is unique up to renaming of the substitutions and of variables. And next, I'll talk about the algorithm to find MGU. The algorithm will recursively explore the two expressions. We can just record what we think and in mind when we are trying to unify two sentences. We scan each corresponding positions of two sentences one side by side. And this is exactly what the program wants to do, but in a recursive way. If we want to design a recursive algorithm, first we have to consider the atomic cases, which is the simplest cases. If either of them is a variable, then we apply the other one to it. If they are identical, there is no need to unify them. If they are compound expressions, we need to break them into lists of arguments and lists of operands, and unify the corresponding position of the list recursively, which is what the point 5 means here. So we have the algorithm when they are the same and either of them is a variable, and if they are compound, both of them are compound sentences, we break them into lists of arguments and compare them one by one. This is done by this line. When we try to compare them, we compare each time for each copy of the recursion, we compare the first element of the list and pass the rest of the list to the next layer of recursion. This process will continue until there is nothing in the list. And we can see there is a procedure in the algorithm, the unified variable. For our imagine, we can implement it using a very normal case. We apply the other term here to the variable. But this idea is not complete, because if one of them is bound to a constant value, then the other element should also be bound to the constant value so that the bindings are consistent. So we add the two lines here. If either of them is bound to a constant value, then we should bound the other one to the value 2. If both of them are not the cases, then we can perform the normal idea of applying one of them to the variable. And if the atomic unification should also check whether the variable itself occurs inside the term. If it does occur, the unification fails. So we add this line. This is the most time-consuming part, and the prologue simply omit this part. And the implementation of tell and ask. The tell operation is indeed a store operation which stores a sentence into the knowledge base, and the ask operation is indeed a fetch operation which returns all the unifiers such that the query unifies with some facts, some elements in the knowledge base. So we can figure out the simplest way to implement tell and ask. When we store a sentence, we can store the fact into a long list, and which perform the fetch operation, we can unify the query with every element of the list. And the previous approach is obviously very inefficient. So we come out with this modification. We put all the sentences with the same predicate into the same bucket and organize all the bucket into a long hash table for easy access. For example, we organize all the nodes fact into one bucket and all the brother facts into a brother bucket. And this bucket is organized in a hash table. We can also perform multiple indexing. We can index the facts by not only the predicates but also each argument in the sentence. And we can construct a substitution lattice, which is to organize the query and the facts in the knowledge base. This lattice has the following property. The child of any node in the lattice is obtained by its parent by a single substitution. For example, if we applied Richard to Y, we got this fact, and if we applied IBM to X, we got this one. And the highest common descendant of any two nodes is the result of applying their most general unifier, as we shall see in the example. If these two sentences are applied the most general unifier, we got the highest common descendant of any two nodes. The efficiency of maintaining and accessing such a lattice is indeed very expensive in theory. And for a predicate with n arguments, the lattice contains this many nodes. And if the function symbols are allowed, the number of nodes will be exponential in the size of terms in the sentence to be stored. But a good news is, in practice, the number of arguments in the predicate is often bounded, so there is no need to worry about this. What we have to do is to maintain the indexes only on keys composed of a predicate plus each argument in the sentence, and there is no need to worry about the n argument. Okay, that's all for today. Thank you.